Welcome to Pratidhwani, where we try to humanize science. I'm your host, GV Pawan Kumar. It's my absolute delight and pleasure to introduce you to my guest on this particular episode, Professor Vijayakumar Chikkadi. Vijay is an associate professor of physics at the Indian Institute of Science, Education and Research, Pune. He also is holding the deputy chair's position at my department. Vijay actually has fantastic research interests, which includes soft and active matter and various different aspects related to how matter behaves not only under equilibrium but also out of the equilibrium and into the systems which have relevance even sometimes in biological situations. Vijay actually has had a very wonderful career trajectory where he was a PhD student at the University of Amsterdam, later on spent some time in France and also in Germany. And we'll hear more about his own career trajectory. And with this brief introduction, I welcome Vijay to Pratidwani.
Yeah, thanks a lot, Pawan. It's indeed a great pleasure talking to you about the science that we're going to do. And please, I'm happy to, I'm glad to be here, actually.
Wonderful, wonderful. This is also kind of the kind of discussion which I am now having nowadays in on my podcast is also to actually look at the research aspect of what individual groups are doing and what individual researchers are doing. And Vijay's own work has been very fascinating. So before we get into the specifics of the research topic, especially the soft and active matter, which is one of the very happening areas in physics today. I would want to also get a brief overview of Vijay's origins and trajectory in terms of career. So, Vijay, give us a little bit about some information about that, please.
Yeah, maybe I can just start from my school days.
Yeah.
Grew up in a very interesting place. It's called Hospete. Probably
Hospital.
you are aware, if you have visited Hampi, then probably the first place that you go to is Hospete.
Hospital.
And from there, it's about 11 to 12 kilometers. So that's where I grew up, spent my childhood, and
That's in Karnataka. That's in
that in
Karnataka in India.
yeah,
Yeah.
yeah, exactly.
Southern state of
Southern India.
yeah, southern India. Yeah, yeah,
I
yeah.
mean, it was amazing, growing up there because on one side, the place was, Hampi is steeped in history, rich history. And on the other side was this Tungabhadra Reservoir, while growing up, I did not realize, how interesting is this place. This place is, but only after moving out of that place, I realized, how interesting this place was. And so that's where I did my schooling. And for bachelor's, I moved to Tiruchirappalli in
Mm-hmm.
Trichy. So that's where I did my bachelor's. And then after that, I was working for a software company, for 2 years. And then, I felt at some point, I felt that, it's too early to start. I was just 21, I guess, when I started working. And then I felt that, I need to spend a little more time studying things, rather than earning money. So I quit the job and then I joined GNCSR as a project assistant, and I continued to
Yeah.
do my MSc there. And after that, I went to Amsterdam for my PhD. And since then, that was the start of my research trajectory, I would say. I've been to a couple of places for my postdoc, and then I returned to Pune to establish a lab here. So, what have been, so I mainly work on soft and active matter, as you introduced. And in particular, what I look at is we use these colloids, fascinating objects, colloidal suspensions as model systems to understand different aspects of soft matter. Even though I call myself a soft matter experimentalist, but the problems that we are trying to understand are have large implications in the sense
Implication.
that we are trying. The reason colloids attracted a lot of attention was, this goes back to Einstein. Actually, all colloidal physicists should thank Einstein for his wonderful paper, where he showed that essentially showed that colloids are pseudo atoms. Okay, so that's
Mm-hmm.
where the colloidal physics was established, I would say. And it took a completely different trajectory. He just wanted to show in that paper atomistic nature of matter um, by computing Avogadro number, estimating the Avogadro number or so. But then, colloidal physics took a completely different trajectory after that. It became a field of research in its own, and people started exploring different aspects. If you directly want to study an atomic system, it was very difficult during those
Mm.
days. I mean, you need to resolve the motion of single atom, which we did not have those sophisticated experimental techniques um, to resolve the motion of single atoms. So that's why colloids became a good toy model to understand a lot of aspects. For example, phase transition, and if you want to look at elastic and then plastic properties of materials. I mean, that's where clothes have played a important role, and then they've been used as building blocks for self-assembly. And in the recent years, I mean, we've been able to synthesize colloids that mimic a lot of properties of living matter. So that's why, so I started my trajectory. I mean, my journey with colloids, looking at colloidal glasses. So this is what a colloidal glasses is. It's just a dense collection of colloidal particles, and then when you are at very high densities, it starts behaving like a solid, and it can you can build you can create a colloidal crystal and then a colloidal glass. Essentially, what you're doing is you're building disordered materials and then ordered materials. And now the interesting thing is we can look at the motion of individual particles.
Mhm.
And yeah, so that's where my trajectory started with colloidal glasses. I mean, the first problem that we tried to address was you put stress on these materials and then how do they deform? And then we know, macroscopically, how they deform. You take any material, you apply stress, you keep applying stress at some point, the material fails. Okay.
Mhm.
So now the question is what's happening microscopically? Can
So
we
one
deform?
second, one second. We'll actually go to those
The
specific
details
aspects.
later. Yeah, yeah.
Yeah, yeah. Because I want to actually unpack it one by one because there might be listeners who might be wanting to know a little bit more about soft matter from a slightly broader
Mhm, mhm,
perspective.
mhm. Yeah, yeah.
So you alluded to the fact that colloids, which essentially are small particles embedded in a media, which actually can be just like proteins in milk, right? That is also some kind of a colloid
Exactly. It's also colloidal.
in a way.
Yeah.
So, Vijay, can you tell us a little bit about what is generally categorized as soft matter? Because that is something which probably we can get started with, and then we'll build upon this intuition and go further and further and come to the problems what you're
Yeah, thanks for that question because many of the students who join my lab, the first question they ask me is what is soft matter?
soft matter. Yeah, yeah, obviously,
So, I
yes,
mean,
yeah.
this is a question that, yeah, I mean, essentially, students do not, they are not introduced to these ideas, in their masters or bachelors, and then when they come for PhD, they're naturally, yeah, curious about what this soft matter is, and then the way I explain them is, soft matter is a system that's essentially, and the elementary units are not atoms, but then these are macromolecular entities, and they self-organize to form different forms, and that is soft matter. And the energy scale that is relevant in these systems is of the order of kT.
Mhm.
And when you try to estimate using the length scales are large, okay, typically let's say it's of the order of micron, and then the energy scale is of the order of kT. And then if you try to estimate from these numbers, characteristic numbers and characteristic energy scale, the shear, I mean, you can try to estimate the elastic modulus for these materials, and that happens to be of the order of few pascals, which means it's a very soft material. You can deform it very easily by applying a small amount of force. And that's a basic definition of soft matter.
Definition.
Then now, within the soft matter, there are several materials that can be viewed as soft matter. Yeah, I mean, extending from synthetic to biological materials, many of these things.
Nice, nice. So it also actually encompasses a very broad category of materials because, for example, from your toothpaste to
Yeah, yeah.
your to any cosmetic items, what you
Gels,
use,
yeah.
yeah, gels, and all the way to tissues, biological matter. They really actually have a very rich variety within them, right? Because that's one of the
Yeah,
reason why
so
it's
they essentially like, it's a macromolecular entity, self-assembled form of like, these macromolecular entities, and then they take various forms.
mm,
Yeah, I mean, many of the day-to-day materials that we use, like, can be classified all food matter, like, and cosmetics, like,
yeah,
so all these things.
yeah,
Granular matter,
wonderful.
for example. Yeah, yeah.
Wonderful, wonderful. So, Vijay, since you actually have exposure of looking at soft matter from various different perspectives, tell us what are all the things which you actually have studied in the context of soft matter. I know Vijay since his master's days because that's when we met each other for the
Yeah,
first
that's where we
time.
overlapped, yes.
Yeah, I overlapped when I was doing my PhD and Vijay was at JNCSR doing his master's, if I'm correct,
Yeah,
Vijay.
yeah, yeah, yeah,
Yeah.
yeah.
And tell us a little bit about the kind of work, because I know that you are also working on fluid dynamics and other kind of questions. Vijay, if I'm correct, you also have an engineering background, right?
Yeah, yeah. I came from an engineering background. That's how I ended up at GNCSR working with Rama on fluid dynamics.
Yeah, Professor Rama Govindarajan is actually a very reputed fluid dynamist, and she's been at it for a very very long time and fascinating work. Yeah, go ahead, Vijay.
Yeah.
Tell us a little bit about the kind of work you are interested in and the questions what you are looking at, and then we'll gradually come to the contemporary questions what you're asking.
Yeah, so I think like I mean during my master's itself, I was working with Professor Mehboob Alam at GNCSR, and then I had started exploring this granular matter, and then after that, like now I moved to Amsterdam for my PhD, and that's where I would say like now I seriously started looking at
Mm,
soft matter. As I said, like, one of the problems that I mean, even now, like, I'm working on it, like, that is disordered materials. I
mm,
mean, you can make models, you can create disordered materials using colloidal suspension. And then the question that we were interested in understanding was essentially the same. Like, you apply stresses on these materials and they undergo deformation, elastic deformation. And then if you apply more stress, like, larger stress, it becomes plastic, which means that once a material has undergone plastic deformation, it cannot regain its original shape. So, like the question for us was, how does it can we understand this in experiments? Can we explore what happens on a particle level? Okay,
mm,
so I mean, as I
mm,
said earlier, doing these experiments with real atomic materials is very difficult because we just don't have those techniques to resolve like individual the motion of individual particles as a function of time and space. So that's why, like, colloidal models became important because we could build models, colloidal glasses. So these are essentially disordered materials. And the technique that we were using was very fascinating. It was confocal microscopy, like, for the first time, or not for the first time, like, it was just then introduced to the field of colloidal science, and then people were trying to understand the motion of individual particles. That's where, like, whole problem became interesting because we could deform this material by
mm.
building a tabletop instrument and then mount it directly on top of a confocal microscope.
Okay.
And we could, as we deform this material, we could record images of these particles at in 3 dimensions and also in time. So that was very
Nice.
exciting for me because, yeah, I mean, for the first time, like, you're being introduced to these kind of techniques. It was very exciting. And once you have, like, this access to this information, then
Mm,
you could do a lot of analysis using that. So once you have the particle trajectories of 100 million, I mean, not 100 million, sorry, it's about a quarter million particles, 250,000. So it's a very large system size. And then once you acquire the data, then it's essentially like, the fun that the fun starts. I mean, of course, like, devising the instrument and then performing the experiment itself is great fun. But then doing the physics, like, getting out the details is even more, it
even
gives
more.
you a different kind of kick, I would say, like, yeah, so there were a lot of studies that had, I mean, I mean, there were a lot of simulations and then theoretical work being done at that point. But when you
Mm,
looked at experiments, there were rarely any experiments on this kind of a topic, like where you had particle dissolved studies. Okay, so
mm,
that's where, like, it became interesting, and we could verify lot of theoretical predictions,
Predictions. Yeah.
kind of well-resolved experiments. Okay, so the sorry.
So in that sense, these kind of experiments, what you do is also related to systems which can be easily probed using a microscopy system, a microscope, right? An optical microscope, and that is one of the
Mm,
advantages
that's one
of
of the
studying
advantages.
advantages of matter.
Yes.
So, Vijay, can you also talk a little bit about why these problems are interesting? Because, for example, understanding, let's say, assembly of colloids,
Mhm.
to first degree, it looks like a simple experiment where you're just looking at something, but there's a very deep physics connected to these things. What is the reason why, let's say, if you take small particles and put them in a fluid and then start looking at their kind of assembly and how they actually interact, etc., etc., can you just motivate us about why these interesting kind of observations are relevant in physics? Could you please tell us a little bit about that? Yeah.
Yeah, sure, very much. So once again, this field of research is very broad in the sense
Mm.
that it's a very interdisciplinary field. There are chemists, physicists working, and then even biology people. And once again, one of the important areas for why colloids is important is you can build metamaterials now, with
Mm.
these colloids. So you can tailor properties that are not available in natural, nature, naturally occurring objects, natural occurring materials. So that's one area. But for me, why it's interesting is, once again, it goes back to this problem that when you look at elastic and then plastic properties of
Mm.
especially disordered solids, you see there are a lot of simulations, a lot of theory, but then when it comes to experiments, there are very few
Few
experiments.
experts,
Right?
yeah.
Essentially the constraint is once again you cannot. There are a few experimental techniques to resolve particle level motion, and that's where colloidal systems become important.
Mm-hmm.
So why is it interesting? I'll tell you. So once again, this takes us back to 1900s, early 1900s. So people were studying the properties of crystals, and then what they realized is there are these defects. All crystals contain defects, so these are lattice imperfections. Then they realized that they play a very important role in controlling the mechanical and electrical properties of crystalline materials. Okay, so these objects, defects, were formalized. What these defects are were formalized way back in the early 1900s. Okay, so that's
Mm-hmm.
almost a century ago, and people knew what these defects are and how they affect the properties of crystals. But now, we are not just surrounded by crystals. There are materials. There are
Better.
several materials that can be classified as disordered materials. Okay, so even a very simple question like what is a defect in a
Mm.
disordered system is still not answered.
And answered. Yeah.
Answered.
Very,
We're
very
still
fascinating.
trying to formulate what is a defect. So whatever ideas that were proposed in the context of crystals, deformation of crystals,
Mm.
can we apply those to disordered materials? And the answer is we are still looking for trying to find an answer to this question. Okay.
Question. Nice.
Yeah. So even after 100 years, that is very motivating me. That is a very motivating thing that, the problems that we are trying to address, these are long-standing issues, and there is no clear answer to these questions. So that
Question.
is one thing I would say is really
Fascinating.
interests me.
In fact, yeah, in fact, see, that's what this is a very important point what you're mentioning, Vijay, because one actually associates in physics, generally speaking, the students get exposed to defects counterintuitively in solid state physics because they actually study this semiconductors because in semiconductors you have defects. Where you can introduce them artificially, and depending upon the kind of doping you do onto the solid state system, it actually can change the property. However, what is not kind of paid attention to, and which is actually equally important, is the mechanical defects, right? Because as you mentioned, if you have group of atoms arranged in a particular lattice, and if you actually have few of the atoms displaced from the lattice position, and then that itself creates some very interesting situation. So if I understand correctly, the colloidal system is trying to emulate some of the physics which is there in such kind of systems where atoms are arranged, and
Yeah,
it's
very
yeah,
nice.
yeah, and as you mentioned that you now have a very nice substitute for atoms, such that now larger particles can now act like as though atoms are arranged. So therefore, there is a very nice kind of experimental probe because atoms are too small to visualize and study. This will give you a slightly different kind of scale, and much easier to look at and manipulate within the microscopic system, if I'm correct.
Yeah, yeah. One of the interesting thing with colloids is, I mean, with these materials is the plastic properties or the mechanical properties are very much universal in a way that, let's say, like you try to deform a colloidal suspension that's disordered, and then you deform it, and then you try to see what kind of patterns emerge in these.
Emergent.
You're
Mm.
looking at deformation patterns. You're looking at local deformations. You're looking at how a particle moves and how its neighbors
Mm.
move, and what kind of fields does it generate, deformation
Generate.
fields does it generate. It's very similar to what you see in atomic solids
Yeah.
also. So many a times what we do is we try to collaborate with simulations to understand certain aspects. And what we have seen is that, yeah, indeed, even though we think, I mean, as I said, like in the beginning, um, even though we call it as a soft matter, but some of the questions that we are trying to understand are very much relevant to a large class of
Class
solids,
of
okay,
solids.
even
Okay.
atomic solids, okay.
Mm. Mm.
So yeah, so that's why some of the properties that we are trying to explore are like universal across different kinds of, especially the mechanical properties are very much universal across different kinds of solids. Yeah.
So one of the key aspects in such kind of studies is to control the interaction uh, or between the particles and between the particle and the environment. So how do you do that generally, Vijay? What are the usual knobs you use to control these kind of interactions?
Yeah, once again, yeah, so this is where colloids are also, have become very popular. So nowadays, not nowadays, it was realized a long time ago that you
Mm.
can tune the interaction between colloidal particles. So
Mm.
one of the famous one of the famous system, one of the system that has attracted a lot of attention is how to induce attraction between these colloidal particles. So
Mm.
the
Mm.
simple idea is you just introduce small polymers,
Mm.
and when
Mm.
you introduce polymers into a colloidal suspension, you call there is something called depletion interaction. So essentially, what happens is when you have two colloids coming close together, there is
Mm.
this area where the colloids cannot penetrate. But then,
Mm.
it's surrounded by colloids on the other side. So there is some sort of a osmotic pressure, that brings these two colloids together. So there is an effective attraction. So this is
Very
how you
nice.
can use, different kinds of. This is how you can induce an effective attraction in the system. And then once again, these colloids are suspended in a solvent, and then you can tune for example, you can add salts, you can change the ionic concentration, and then you can make, typically, when you have colloids that are due to chemical synthesis, they carry a certain amount of charge, so the electrostatics also play a role. By introducing these salts and then playing with the ionic concentration, you can tune those interactions very nicely. And
Fascinating.
yeah,
Fascinating.
in addition to that, you can also make colloids of different shapes.
Shapes.
Yeah.
Okay. Okay.
So I mean, yeah. So this is where, this whole field becomes interesting. So now
Interesting.
you
Yeah.
can build metamaterials.
Yeah.
The shapes that are not naturally available in nature. Okay, so you can make funny shaped particles and then try to see how they self-assemble and what kind of emergent properties do they give rise to.
Give
It could
rise
be
to.
chemical properties or it could be mechanical properties. Yeah, so that's where it becomes. Yeah.
Wonderful, wonderful. So now that you actually take such kind of colloids, the colloids themselves actually are made of certain materials. What are the general typical kind of materials which are used for to make such colloids? And there's also a plethora of colloidal materials which have very interesting property. because the surface actually plays a critical role, right? Because you need to have most of the interaction kind of at the interface. And given the fact that as you shrink the size of the structure, the surface to volume ratio keeps increasing, which means that most of the stuff, what happens is essentially happening at the interface. And therefore, the interface becomes such an important point related to all these kind of materials. So, what kind of composition and what kind of materials are used, Vijay, for these kind
So
of
yeah,
colloids?
typically, so once again, if I talk about
Mm,
simple colloids, I mean, these can be silica material. I mean, silica, it
mm.
can be made of silica, or it could be made of polymer like
Polymer, yeah.
aluminum
Mm,
or polystyrene. So these
mm.
are elementary, simple ones. And in the recent years, people have come up with different ways of making, as you are referring to, you can functionalize these particles, you can functionalize the surface, and you can half coat these particles. In the sense,
Mm.
you can make genus particles that have different functionalities. You have a single colloid, and one half of it is coated with a different material, the other half
Material.
with a different material. Now, you're breaking the symmetry in this, and then with this, you can tune the interactions. I mean, a lot of things actually. If you apply an electric field or a chemical gradient, then you can set up a flow around this particle, because you can make one half of this particle reactive to the chemicals that are present in the solvent, or you could excite this one half of the particle with a laser and then heat it up and change the local temperature just on one side. So this will once again give rise to different kinds of flows along the surface, and then you have a self-propelled particle. And this is something that has found a lot of applications in yeah, nowadays. Even your group is working on it. So now we have the self-propelled particles, and you want to build synthetic models of active systems, or systems
I'll
that
come to that. I'll come to
are.
that. I'll come to that. This is actually a nice segue to actually also relate to that part of it. Before we come to that particular point, I want to emphasize a little bit on the kind of problems your group is working on, and you can also give an introduction to the kind of questions you have been asking, and then we'll also get into the active part of your own work, and that would actually give us a nice lead into the problems. Yeah. Yeah, tell us a little bit about that point, Vijay. Yeah.
Yeah, about the active matter you're saying, or
Yeah, no, the kind of problems what your
the
group is
problems? Okay,
actually
fine.
working. Yeah, and that probably surely includes the active matter too. And then we'll come to the active matter part of it.
Yeah, once again, yeah. So one of the problems that we are working on is once again defects, creating. So what we have recently done, some of the recent things that we have done is we've been looking at how to identify defects in these kind of systems, especially disordered colloidal systems, and then also ordered colloidal systems. How do we define defects? Since we have information about how these particles are arranged in 3D space, and then how they also move when we apply stresses. Now, so once again, one of the important problems that we've been trying to address is looking at the structure of these systems, can we identify defects? What I mean by
Mm,
that is when I apply stresses on these materials, the material is going to fail in certain regions. Okay, so now, even before they fail, can we look at the structure, microscopic structure, and then try to say that this is where my defect is, and this is where the likelihood of the material failing is large, is something that we want to predict. Okay, so these are the kind of questions that we've been trying to answer. And so one of the reason, so this is relating to structure,
mm, mm.
relating structure and then the dynamics. And one of the things that we did was collaborate with our neighbor, Sarika. She was she was working on a related problem, how to relate structure to dynamics in classes. And
This
now,
is Dr. Sarika Bhattacharya at
yes,
National Chemical Laboratory in Pune, which is just beside the IISER Pune.
yes,
Yeah.
we were just lucky to be her neighbor, and she was working on these problems where she was trying to work on a microscopic theory to understand to relate structure and dynamics, and then she came up with an idea that you can define something called an effective potential. You have a particle, and then you have neighbors. Depending on the distribution of the neighbors, can I associate some sort of an effective potential? Because this particle cannot move, it's arrested by the neighbors. As I said, it's a very dense suspension. So the particles are very closely packed. So if you have a particle and then it's packed by the neighbors and this particle cannot escape, it's jiggling. It's it's arrested. There's an effective potential that is created by the neighbors, and this particle is essentially trapped in that effective potential. So that is a kind of picture that they developed, and now we felt that can we extend these ideas to or colloidal suspension? Can we use this idea to identify structural defects in amorphous systems? So when I apply, the stresses, these regions, localized regions are going to fail. So can I associate an effective potential to these regions? So if a region has a lower effective potential, smaller effective potential, in the sense that the depth of the caging, the potential is shallow, then those particles will escape out of the cage when you apply stresses very easily. And then this idea was very successful, and then we could indeed show experimentally that this is what happens in these systems. And yeah, so thereby, we showed that some of these ideas that were proposed by Sarika could be applied to colloidal suspensions, and then it gives rise to a very nice definition of what these defects are in. By looking at the structure, you can define defects in these systems. That is one interesting work that we did in the last few years. We are still trying to understand this in deeper. The other thing that while we were working on this problem, we also learned that there are other groups. For example, in Italy, there were these group of people who were trying to understand the same problem from a topological perspective.
Yeah.
So if you have liquid crystals, they have orientation, they have natural orientations, and then by looking at the topology of their orientations, you can define defects. Okay, so in these materials. But now, in glasses, there is no orientation. Okay, so now how do you define topological defects? So they said that instead of looking at, you look at the displacement of the particles. When you apply stresses, you look at the displacement, how these particles move. These are spheres, not rods, but how do these particles move? And based on that information, then if you associate vectors to their motion, you have orientational field. And using this orientational field, one can define topological defects, like the way they do it in liquid crystals. And this has been amazing. I mean, this was an amazing idea. And now the interesting thing is you are defining these topological objects. And even if you go back to crystals, so the way the defects are defined in crystals are also they're also topological objects. So there is a one-to-one correspondence between these topological objects and those topological objects. And now the big question is how far can we go with these ideas to show that the topological defects in glasses can be compared to the topological defects in crystals.
Okay.
Nice. So this is where we did these experiments with tweezers, and thanks to you, we were able to do the. We create an optical vortex and then create deformation fields within these colloidal suspensions. And when we created these deformation fields, we saw that indeed, if you use the displacement vectors of the particles, you can identify topological defects in the displacement field of the colloidal particles. And we could we could associate charges to these topological defects. So essentially, the defects are +1 defects and then -1 defects. And the whole picture is very new. This picture was existent even before also, but now, we are able to do a lot more quantitative things with these topological defects. And that the topological defects are created when there is a plastic deformation, and when the system relaxes, there is annihilation of topological defects. And what drives the plastic deformation is the interaction between these topological defects. So all these things, we've been able to quantify in a very nice way, and that's really a big surprise for me that it works so nicely. Yeah.
Fascinating. So this is a one set of problems. This has also led to some very, very interesting papers from Vijay's group, which I am anyway linking his web page. So his publications can also be kind of explored on his web page and also on his Google Scholar page. So tell us a little bit about this paper which came out recently in PNAS, which is Proceedings of National Academy of Sciences in the USA, which actually looked at these very interesting categorizations and looking at these kind of colloids from a viewpoint of dense suspension. And what is the question you people were trying to address in that particular
Yeah,
paper?
this is the same question that I was
Yeah,
talking
yeah.
a few minutes ago. So once again,
Yeah.
this was done in collaboration with Sarika, who is at NCL. So had proposed this idea that
Mm.
you can link structure to dynamics
Dynamics. Yeah.
by
Mm.
defining something called an effective caging potential. So this is
Mm.
once again a dense suspension. If you have a particle, it's essentially caged. The motion of this particle is arrested by the presence of the neighbors.
Mm.
It's a very dense system. So you can think in terms of an effective potential. So the neighbors create an effective potential, and this particle is essentially trapped in that effective potential. And we extended those ideas to colloidal suspension, and we were able to show what these structural defects are in colloidal glasses. Okay, so we showed that
Nice.
when you apply stresses on these materials, the material fails, and then we could associate these material. We could show that the effective potential corresponding to those regions was smaller compared to a region that did not fail. A stable region is associated with a deeper caging potential
Hmm.
compared to a region that fails very easily under stress. So these were some of the ideas that we could, I mean, I think this was probably a first experimental demonstration of structural defects in colloidal glasses. Yeah,
Classes.
where we
Nice.
could show it in an experimental system that
Say so.
what these structural defects are.
Wonderful, wonderful. So your group also looks at the broader system of active matter. So first of all, define what is active matter for us, and second, tell us what you are working on active matter.
Yeah, active matter. What is active matter? My own definition has changed a lot over the years. So, I mean, I started working on active matter in 2015, so it's been about 10 years now. And yeah, initially I just thought that these are active matter is comprised of elementary units that self-propel.
Hmm.
Okay. And I mean, over the years, I've discovered so many more models of active matter because you have active matter field theories. Okay, so
Hmm.
when you go to a field theory, there's no more particle. Okay, so but
Yeah,
still,
yeah.
those models describe active matter. Okay, so yeah, it's been my own definition has changed, but I mean, there are some things that are very important. Like now, when I try to define a system as active matter, it's essentially out of equilibrium, which means that you don't have time reversal symmetry, and
Hmm. Hmm.
you don't have these detailed balance that are cornerstones in equilibrium statmech. So these things are violated in active systems. Uh, and there is local injection of energy. Okay, if I think of colloidal suspension on on a particle level, there is injection of energy. There's local injection of energy. I mean, you can take a system out of equilibrium in many different ways. For
Hmm.
example, you can heat the boundaries. You can have a flow, I mean, system and then heat the boundaries. So you are essentially injecting energy at the boundaries. Okay, that is also a non-equilibrium system. But then the active ones, what I'm saying is that we have to inject energy at a particle level.
Hmm. Hmm.
And example could be your the kind of particles that you are looking at, and even some of we've been studying these Janus colloids.
Bullets, yeah.
And if you shine light, there is a chemical reaction on one side of these are colloidal particles that have two different functionalities on one half of the particle, on the other half of the particle. So one half of the particle, when you shine light, there is a chemical reaction that is going on this side, and this creates a layer of flow, and that
Hmm.
circles the particle. Okay, so there, once again, the injection of energy takes place on a particle level. So that is what I mean by local injection of energy.
Energy. Okay.
It could be a
Okay.
lot of even biological systems. There are these motor proteins that inject energy into the system on a local level, at local level. Okay. And yeah, so this is what I mean by local injection of energy. And the third thing is this injection of energy should lead to some motion or forces. It should generate forces.
Yeah.
So
Yeah.
these are the three things I would say I would look for in an active system. Yeah, so that would be once again yeah, this is a very broad way of defining active matter systems. You may not have particles essentially, but you could have even biological systems
By
where you don't
systems.
have particles. I mean, you have local chemical reactions, ATP and GTP, that are generating the energy. It could be molecular motors that are generating motion. Yeah, so yeah.
Fascinating. So, in that sense, the categorization of active matter can be either synthetic active matter, which means human beings can actually make them in the laboratory, or one can also look at active matter which is biological in nature, which means that the evolution has taken care of its own kind of, the new forms and other kind of things which has evolved over a period of time. So, this. I know that in your lab you study the first kind of active matter, but you also have been able to combine the synthetic active matter with biological matter, in the specific case, bacteria. So
Yeah.
tell us a little bit about the problem and the question you and your lab is trying to address in the context of active matter, where you are combining these two kind of entities.
Yeah, so yeah, it's an interesting thing. Like now, if I think, how did I start get into this biological active matter in the sense we are working with bacteria. So this goes back to when I came here, 2017. We did not have lab, and I ended up working with Umakant. He had an optical setup. So we thought, okay, so let's look at some active matter thing because it doesn't cost you too much money. Okay, so bacteria cost
Yeah.
any money. So that is the cheapest experiment that I could do. Okay, so we found out bacteria, and then one of the problems that we wanted to understand is measuring viscosity of a suspension, bacterial suspension. Okay, so even before we do that, we just wanted to set up the on optical tweezer. You have this two-point microarchaeology that was very popular to measure viscoelastic modulus and then shear modulus of soft systems. Okay, so these were techniques that were established, very well established technique. Um, and we essentially wanted to try along those lines, set up a tweezer and first, start looking at the kind of fluctuations you have in these systems. And unfortunately, that turned out to be too ambitious to start with. Actually, measuring, setting up a two-point microarchaeology using an optical tweezer, wherein you have two traps, and then you look at a port of one of the trap, and then look at the response of the other one. That turned out to be a little too ambitious to start with. So we went back to a simpler problem. We said okay, let's look at a single colloid within a bacterial suspension. And that's how my journey started with biological active matter, I would say. Um, so one of the problem people had studied a lot, single particle properties within an active system like bacterial suspension. So there are these very famous papers by Liebschaber and company. So now we felt that people had not really explored higher densities. When you have many particle system, what happens in these systems? How do these particles how do these systems behave? So that was the motivation, and then we started. That's one of the first problems that we wanted to understand. You have many particles, many colloidal particles. Now, what happens to this? And what we find is surprisingly that the activity or the presence of the bacteria gives rise to an active depletion force, which is a yeah. So we found that the particles, suddenly start to make clusters, and these clusters are not static clusters. but very dynamic in the sense they form, they break, they form, they break. And this is what we tried to understand. We started collaborating with Shraddha Mishra at IIT
Mm.
BHU. They were doing the simulations part. In fact, that problem was motivated by what they had studied in simulations, actually.
Simulations. Okay,
Yeah, so that
nice.
gave us an idea. So, okay, let's start looking at these aspects, effective interactions between colloids in the presence of in bacterial suspensions.
Mm,
How
mm.
these interactions modify, like now, what does activity bring new into this? Is what we try to understand. And later on, we published a paper in PRE, and then
Mm.
that gave us many more ideas. We wanted to understand that these particles come close together. I mean, it's like if you have a homogeneous suspension of colloids in a bacterial
Mm.
suspension, it's not stable. They start to form these I mean, they form these clusters.
Clusters,
We
yeah.
started understanding it resembles some sort of a phase separation.
Mm,
Okay,
mm.
so if you try to mix oil and water, they don't mix well, right? I mean, so oil will form a different phase and water will form a different phase. There is phase separation. So something similar was happening even in these systems. The colloids were coming together, forming a cluster, and
Mm.
it looked like a phase separation. But this phase separation is not in equilibrium. Okay, so it's in a not out of equilibrium system, because these colloidal particles are now suspended in a bacterial suspension, and then the suspension is far from equilibrium. Okay, and so this is what led us to understand this question of phase separation in active systems. How is it different from phase separation in equilibrium systems? So
Nice.
equilibrium systems the phase separation in equilibrium systems has been studied a lot, or I mean, it has a long history. Now, when you talk about this kind of system, wherein you have a passive phase and then active phase, how does phase
Mm.
separation occur? I mean, there are not many studies, and we discovered a lot of things. Once again, we collaborated with Shraddha and then Sanjay Puri. So those are the people who are looking at phase separation aspects in active systems. And the fascinating thing is, the one thing that you could study is how do these structures coarsen? How does the length scale of these structures grow as a function of time? You start with a homogeneous configuration. Now what they do is they start to come together, form clusters. Now we try to understand how these clusters, the size of these clusters, grow as a function of time. Okay, and then we found that these exponents are very different from what you find in equilibrium systems. And the other thing that we found interesting was if you it's a phase separation. You have one phase, you have another phase. Okay, so the phase boundaries in equilibrium systems are typically very sharp,
Mm. Mm.
very well defined. But now, when these colloids form a cluster, like if you look at the boundaries, the phase boundaries, they are very rough. And then we try to characterize them, and then we found that they're actually fractal-like structure.
Wow, very interesting. So
Very, very
fractals are,
interesting.
yeah, very, very fascinating. Yeah.
Yeah, very fascinating. And then we went back to Shraddha and Sanjay. We asked them, whether you can cook up a model, that could
Mm.
explain these things. And they were, indeed successful in coming up with a model. This is essentially called Model B. Model B is something
Mm.
that is used for equilibrium systems, to understand phase separation in equilibrium systems. And you have Model B, and on top of that, you have a colored noise. So essentially, the colloids are suspended in a bacterial suspension. The bacteria is giving kicks to these particles, and this kick is very different from a kick that a particle receives in an equilibrium bath. It's a colored noise. It's not like white noise, but it's a colored noise. So using these ideas, they were able to propose a model, and that model could explain many of these interesting things that we were that we were finding in experiments. So yeah, so this way, it started as a small experiment to, we essentially didn't have too much money to spend, bacteria were a very cheap system to work with, and then that's where we started with, and then now we are at a stage where we are trying to understand phase separation aspects in active systems, and trying to understand how these are different from equilibrium systems. What is the novelty? And then what I believe is just we are scratching the surface. There's much more to
Yes.
discover. Yeah.
Fascinating, fascinating. In fact, it also tells you that there are very interesting problems to be explored within the laboratory situation at a very high degree of rigor, uh, even at a cost which need not be like extraordinary. This is one
Yeah,
of
this
the
is something
few
that
examples.
this
Yeah.
is something that I tell my students, soft matter research is sustainable.
Sustainable, exactly. You're absolutely right.
Because I mean, we
Sustainable.
can do very interesting stuff, very new stuff. Like, all this is like, at the, these are not things that have not been answered for 100 years, but I mean,
Yeah.
these are new things that are coming up,
Coming
so
up, yeah,
yeah.
you're absolutely right. Second point is also it segues into sustainability problems too. In fact, there are so many questions related to environment and the physics of the kind of materials which is associated with the environment. Because most of the systems, as you correctly mentioned prior, that they are not crystalline in nature. Majority of them either are totally disordered or it has some partial order, but for sure they are not in crystalline in nature, because even if you take, let's say, the table or any kind of material, including, let's say, the devices what we use, they have been prepared using some kind of mixture of materials. Therefore order, disorder, and adding flexibility to such materials, these are all very critical issues in soft matter physics. So, Vijay, can you also give us a kind of an overview of what is the kind of work you expect students to do in your laboratory? Because I know you have various different interests within the soft matter. It would also a good introduction for somebody who would want to, let's say, work with you or try to understand the problems what you're working on and what kind of stuff you would want to do going forward.
Yeah, typically, so if you want to work if a student wants to work in soft matter, like in essentially
Mm,
what we in terms of physics concepts, mainly like we are using our understanding of statistical mechanics and condensed
mm,
matter is
mm,
what we are using. So we are trying to understand uh, many body systems, the collective behavior, the emergent properties in these soft matter systems. So I mean, essentially, yeah, this falls under like stat mech and then condensed
mm,
matter. These are the so if somebody is interested in stat mech and condensed matter, they should give a chance to soft and active matter. There are amazing problems and problems that are at the forefront of the physics. So the developments in sub areas. Okay, so that's what I would say. These are the, I mean, yeah, those are the kind of problems that we are trying to understand. And yeah, so what do they do is essentially, I mean, one of the most sophisticated experiment that we have done is, of course, the optical tweezers
mm,
generating an optical vortex and create, I mean, simple instrumentation to build a tabletop shear cell. And
mm,
then what we're trying to explore now is with Shiva Patil. Shiva has deep interest in force spectroscopy. He does a lot of work with AFM, like how to measure the forces. So we want to borrow some of those ideas and implement them in our system so that we can build a rheometer. So right now, like we have a shear cell that applies only a controlled shear on
country.
the system. So now the question is like can we also measure stresses in the system by incorporating some sort of a force module? So that is one thing that we are working on. And typically, a student who joins the lab, like he gets introduced. I mean, he gets trained, and so when Rati joined, like for example, Rati Manasi is one of the second PhD student from she'll be graduating soon. She built this optical tweezer,
Mm,
and when Pragya was the first student, and then what she did was she was the one who introduced the biological systems into the lab. Like she learned how to culture the cells and how to work with the cells, how to create a robust system wherein we can so typically, like these are living systems. I mean, they die within no time if you don't give
mm,
them
mm,
food. Okay, so how do you make them survive for let's say like an hours, 4 hours, 5 hours, and then you're also doing. I mean, they also need oxygen to survive. Okay, how do you keep them alive for a long time? So how do you build a setup? to take care that we can do experiments for 3 to 4 hours. Like, how do you fine tune those experiments? So this is what Pragya did, and then she did a fantastic job, and that has laid like a platform for the future students to who are coming to the lab. Like, they can learn
Leonard.
and like carry on those things. And Rati is, I mean, she built a shear cell, as I said, like, if we are looking at these sheared colloidal suspension, wherein we're trying to understand the structural defects yeah. So for those studies were done using a shear cell, and we need to, she built a shear cell when she joined the lab. And that was something like, we knew since I had done previously, I could give her some ideas how to build this shear cell and all.
Mm.
But what she did independently was optical tweezers in collaboration with you. Like, I was new to optical tweezers. I knew, like, few things working in Umakant's lab, but then Rati really took it over, and then she built this. Essentially, she had this interest, like,
Yeah, yeah.
so the lab is driven by the interest of the students, I would say.
Mm.
Like, she built up this optical tweezer, and then once again, like, she's laid a good platform for the future students to come and learn. And as I said, like, one of the things that we want to build in the future is turn our shear cell into a rheometer. And yeah, we want to do many more experiments with optical tweezers. So there are a lot of ideas that are being proposed by, for example, Shorjit Karmakar in TIFR.
Mhm.
So they have these very wonderful ways of looking at pin system. You can pin and then, like, also shear, and then you can control the mechanical properties by pinning. So can we implement some of those ideas, pinning ideas, into our systems? Is something we are trying to explore using optical tweezers. So yeah.
Fascinating, fascinating. This actually gives a very beautiful overview of a lot of questions what you and your group are asking. It also actually gives an overview of the contemporary aspect of soft matter physics because it also is deeply connected to statistical physics, and there's a room for various different kind of sub-disciplines of physics to come in. For example, optics and soft matter interface is also very fascinating because if you look at all your displays, it has liquid crystals in one form or the other. And in order to understand how that interacts with light and be utilized for various applications is a contemporary research problem. So thank you,
Yeah.
Vijay, for
Yeah,
this
just one more thing.
very
Like,
yeah, yeah.
yeah. So I mean, the other interesting thing about soft matter is it's possible for this. It's possible to combine both theory and then experiments together.
Experiments, yeah,
That is
yeah.
one of the fascinating things that I see here. So even typically, I've seen students. It has not happened in my lab. Maybe it will happen sometime very soon in future. Uh, PhD student working both on theoretical aspects, cooking up theoretical models, and also,
Yeah.
like, doing experiments. This is something that was done very regularly in one of my previous lab where I
Mm.
was. Students were working both on theoretical aspects and experimental aspects. So there could be a marriage between these two things, which is a little difficult to imagine in others areas. Like, for example, if you're doing some complicated experiment in condensed matter, like, it's very
Yeah.
difficult to do both. But in active matter, I hope that this is still possible, and then that opens up. It just makes the problem interesting if you're able to do experiments and also understand it theoretically, like, do quantitative stuff. That's something like, it's very satisfying. So that's one of the interesting aspects of soft matter that has attracted me a lot. Like, I mean, that has attracted me and then other people. Yeah.
Fascinating, fascinating. That aspect of kind of combining theory and experiment is so central. In fact, even in optics, this is a very strong kind of encouragement to go in that direction because there again the theoretical foundations are reasonably well laid. At least in the classical electromagnetic sense, there's a lot of interesting things one can do. So, Vijay, thank you very much for this very nice overview of a lot of interesting work related to soft matter. You have literally unpacked soft matter for us in a
Yeah,
way. And
thanks, Ron. Thanks. I mean, it was nice talking to you too, and I mean, it was nice collaborating, I mean, with you over the years. Yeah.
yes, yes. In fact, I've learned a lot from Vijay and Vijay's group because they have a very good set of people, and my own students have largely benefited also by interacting with Vijay's group. And I'm very sure we'll continue to actually learn a lot from very fascinating work which is going on in Vijay's lab. And I
Yeah,
wish you
that's
all the
also what I
best.
would say. Each
Yeah.
other, learn
Yeah,
from each
yeah, yeah,
other.
yeah. It's a mutual. It's always the mutual thing. And so I wish you and your research group all the best going forward. Thank you very much for your time.
Thanks, Paul.
This is Pratidwani, where we try to humanize science. This time we unpacked soft matter physics with Vijay Kumar Chikkadi. Thank you, Vijay.
Yeah, bye.